A week ago, SpaceX blew up Booster 18 during a high-pressure test. The liquid oxygen tank buckled inward. The top section split like a torn can. Debris scattered everywhere. Everyone expected Flight 12 to delay until late 2026. But 2 days later, SpaceX started laser-cutting the wreckage. No waiting, no panic, just immediate action. How does losing a $50 million booster not derail their timeline? And what does Boeing's Starliner cancellation have to do with this? Welcome to Space Update 24 Hours. Let's dive right in. The scene at Massey's test stand looked like a war zone. Booster 18 sat there one moment, going through what seemed like another routine pressurization check. The next moment, the entire structure buckled inward with a force that sent shock waves through the facility. The forward dome deformed instantly. The methane tank section hung open like a gutted building. Insulation dangled off in strips, frozen solid from the cryogenic fluids that had just been inside. Because the booster was fully loaded with liquid oxygen and methane when it failed, the blast zone turned into an ice field. Cleanup crews couldn't even approach for hours. The whole area was a frozen disaster site scattered with twisted steel and broken equipment. Most industry analysts immediately called it. Flight 12 was done for early 2026. B-18 was supposed to carry Ship 39 into orbit in just a few months. Losing a fully assembled booster at this stage typically means at least a 6-month setback, sometimes longer. The math seems simple. Build a new booster, test it, integrate it, repeat all the validation steps. But what happened next caught everyone completely off guard. How could SpaceX possibly maintain their timeline when tens of millions of dollars just turned into frozen scrap metal? 2 days after the explosion, the forward section was already being cut apart. Workers brought in industrial laser cutters and sliced through the upper methane tank section like it was sheet metal. Once detached, cranes lowered the massive piece to the ground. Then they chopped it into 3 large segments, including the hot staging ring that sits between the booster and ship. Even in pieces, each chunk measured 9 meters across. Moving them required careful coordination, heavy equipment, and hours of slow, deliberate work. This wasn't cleanup. This was surgical demolition executed at a pace nobody expected. The lower section, where the liquid oxygen tank failed, faced an even harsher fate. That entire portion is being cut into smaller pieces because there's nothing salvageable left. The tank walls are warped beyond repair. The structural integrity is completely compromised. You can't reuse stainless steel that's been subjected to that kind of catastrophic failure. The metal itself might be recycled, but as booster hardware, it's worthless. And here's the brutal reality. Stainless scrap metal barely sells for anything these days. Booster 18, which likely cost somewhere between $50 to $70 million to build, is now worth maybe a few $1,000s in scrap. That's the price of pushing the envelope in rocket development. But here's where things get interesting. While B-18 was being dismantled, Ship 39 was still moving forward. This Block 3 upper stage has already passed its early build checks and is now positioned for full cryogenic proof testing. All the ground hookups are in place. All the fuel lines are connected. The ship is basically sitting in a ready-for-cryo position, waiting for SpaceX to give the green light. It hasn't received its Raptor 3 engines yet, but that's standard procedure. SpaceX always completes cryo testing before mounting engines to avoid risking expensive hardware during structural validation tests. So Ship 39 is progressing on schedule, completely independent of the booster situation. The question is, what booster will it fly with? This is where Raptor 3 becomes crucial to understanding why SpaceX isn't panicking. Block 3 ships like Ship 39 were designed from the ground up to work exclusively with Raptor 3 engines. These aren't just incremental upgrades from Raptor 2. They represent a fundamental redesign of how methane rocket engines operate. Raptor 2 produced around 230 tons of thrust, which was already impressive for a Methalox engine. Raptor 3 reached over 350 tons during full testing. That's more than a 100-ton increase from a single engine. For context, that extra thrust per engine means fewer engines needed overall, which reduces complexity, weight, and potential failure points across the entire vehicle. The chamber pressure jumped from around 300 bar in Raptor 2 to nearly 400 bar in Raptor 3. Higher chamber pressure means the fuel burns more efficiently, producing more thrust from the same amount of propellant, but it also means the engine has to withstand extreme internal forces without failing. Raptor 2 sometimes struggled with this during multi-burn missions. The ignition process was sensitive at high pressures, making repeated burns in space unreliable. Raptor 3 solved this with a completely redesigned ignition system that's far more robust. This isn't just about power, it's about reliability during the orbital refueling missions that Starship will eventually need to reach the Moon and Mars. Can you see why losing B-18 might not be as catastrophic as it initially seemed? SpaceX rebuilt Raptor 3 to be simpler. They removed complicated plumbing networks. They eliminated delicate components that made Raptor 2 harder to manufacture and maintain. The result is an engine that's easier to produce at scale, more powerful, and more reliable. This is the engine that will power every Block 3 ship going forward, including Ship 39. And this is why Block 3 ships look physically different from earlier models. The engine bay is redesigned. The thrust structure is reinforced. Everything about these vehicles is optimized for Raptor 3's increased performance. So what's the actual plan for Flight 12 now that B-18 is gone? The immediate replacement is Booster 19, the next unit in the production line. Right now, all of B-19's sections are sitting inside the Star Factory as separate ring segments and subassemblies. Soon they'll be rolled into Mega Bay 1 for vertical stacking. The entire stacking process typically takes about 1 week if there are no major complications. If everything goes smoothly, B-19 could be ready for its first cryogenic proof test by late December or early January. That timeline is aggressive, but it's not impossible. SpaceX has done it before, but here's the reality check. A successful cryo test doesn't mean the booster's ready to fly. After cryo testing comes static fire tests, where all the engines are ignited while the booster is held down to validate thrust levels, fuel flow, and engine performance. Then there are full systems checkouts, integration tests with Ship 39, and final flight readiness reviews. Even though SpaceX officially states that Flight 12 is still scheduled for Q1 2026, nobody knows if that means January, February, or March. If it slips into April, technically that would miss the goal. But given the complexity of Starship and the fact that a booster literally exploded during testing, a 1-month delay would actually be remarkable, not disappointing. The real question is, how is SpaceX maintaining this pace when every other space company would need a year to recover from this kind of setback? While SpaceX demonstrates this level of operational resilience, Boeing is experiencing the complete opposite. After years of delays, technical failures, and the disastrous 2024 crewed test flight, NASA has officially canceled Starliner's upcoming crewed missions. The program is effectively grounded for the foreseeable future. This isn't a sudden decision. Starliner has been struggling since its very first flight in December 2019. During that uncrewed orbital test, the spacecraft's mission timer malfunctioned by 11 hours. Because of this error, the capsule fired its thrusters at the wrong time, wasted fuel, and never reached the intended orbit. It couldn't dock with the ISS and had to return early. NASA later discovered over 80 software errors in the system, 80 separate coding issues that somehow made it through Boeing's quality control process. Boeing tried again in May 2022 with another uncrewed test. This time, Starliner reached orbit and completed docking. But 2 propulsion valves failed during the mission. Several thrusters underperformed. The vehicle experienced cooling system problems. The flight was technically successful, but the issues kept piling up. Then came June 2024, the first crewed test flight that was supposed to prove Starliner was ready for operational missions. 2 astronauts launched aboard the spacecraft, and almost immediately after reaching orbit, engineers detected 5 helium leaks in the service module. Helium pressurizes the propulsion system. Losing it means the spacecraft can't maneuver properly. At the same time, 5 maneuvering thrusters failed during approach to the ISS. Several more showed erratic performance. The crew had to manually control the spacecraft to complete docking because the automated systems weren't functioning reliably. The astronauts were supposed to return after 1 week, but the thrusters remained unreliable. The helium leaks continued worsening. NASA made the call. It wasn't safe to bring the crew home in Starliner. The spacecraft undocked empty and landed autonomously in September 2024. The astronauts stayed in orbit for 9 months before SpaceX launched a Crew Dragon to retrieve them. Starliner, the vehicle specifically designed to transport crew to and from the ISS, couldn't complete its primary mission. What does that tell you about the state of Boeing's space program compared to SpaceX's ability to recover from a booster explosion in less than a week? Because of this failure, Starliner won't fly any astronauts in 2025 or early 2026. The next scheduled launch in April 2026 will carry cargo only, assuming Boeing can even meet that date. NASA's original contract promised 6 crew rotation flights. That's now been reduced to 4, and even those are only guaranteed if Boeing can restore confidence in the vehicle's safety and reliability. The contrast couldn't be sharper. SpaceX loses a booster and immediately pivots to the next unit without missing a beat. Boeing's spacecraft fails to bring astronauts home, and the entire program grinds to a halt for years. One company treats setbacks as temporary obstacles. The other treats them as existential crises. So what's the real story here? SpaceX just showed us something the aerospace industry has never seen before. A company loses a $50 million booster in a catastrophic explosion, and within 48 hours, they're already cutting it apart and moving forward with the next unit. No months-long investigation, no program freeze, no panic, just immediate action and adaptation. Meanwhile, Boeing's Starliner fails one crewed mission, and the entire program gets shelved for years. NASA reduces their contract. Astronauts get stranded for 9 months. The difference isn't just about technology, it's about culture, pace, and how you respond when things go wrong. Flight 12 is still targeting Q1 2026 with Booster 19 and Ship 39. That timeline seemed impossible a week ago. Now it's looking increasingly realistic. SpaceX has fundamentally changed how we think about rocket development. Explosions aren't program-ending disasters anymore. They're data points, learning opportunities, and temporary setbacks that get resolved in days instead of years. What do you think? Can SpaceX actually pull off Flight 12 in Q1 2026? Or will Booster 19 face unexpected delays? Drop your predictions in the comments below. If this breakdown gave you a new perspective on how these two companies operate, hit that like button and share this video. And if you want to stay ahead of every major development in space exploration, subscribe to Space Update 24 Hours and turn on notifications. We'll see you in the next one.